Okay, so last time we've been talking about the coherent states of the harmonic oscillator. Oops. Which are labeled by a complex number alpha. And we learned last time that the magnitude of this thing is very large if you're talking about a macroscopic harmonic oscillator. In fact, that's sort of what a macroscopic harmonic oscillator is. It's a coherent state with a very large magnitude. So for oops. Every once in a while, my Apple Pen decides I want to draw a straight line, and I don't. For macroscopic. Okay, and let's suppose that that is actually going to be the wave or the ket of our state at time t equals 0. And then at time t, the ket will be this. It will be an irrelevant phase, one that we can't observe, times a different coherent state because the complex number will have changed from alpha to alpha multiplied by a phase that's not irrelevant. And then last time we figured out the expectation value of x in such a state is nothing other than what a classical person would say is the time dependence of a classical harmonic oscillator. It just oscillates back and forth. And similarly with the expectation value of the momentum. So it's minus m omega times x naught times a sine. So it's oscillating out of phase with the position. This is exactly what classical physics would tell you. Okay, and I wanted to mention that more generally, this is an example of Ehrenfest's theorem in action. Ehrenfest. Okay, and Ehrenfest's theorem is something that we proved in general on September 28th. I had to look it up because I realized that for some reason it didn't make it into the PDF notes for this class, which was an oversight of on my part. And so to compensate, there is now a note, one-page note on the course webpage. And if you want, you can go look at the YouTube lectures for that as well. But I think it's probably easier to just look at the one-page note. And one of the reasons I'm bringing this up is because it's mentioned on problem 2 of homework set 7. So you do need to know what it is for that. And so in general, what happens here is Ehrenfest's theorem says if I take the time derivative of the expectation value of an operator, in this case x, that's minus I over h bar times the expectation value of the commutator with the Hamiltonian. And so in this case, we know what our Hamiltonian is. And the only part that matters for the commutator with x is the p squared over 2m part. So this is x commutator with p squared times 1 over 2m. The part that depends on x just commutes with x, so that doesn't do anything. X commutator with p squared is 2 I h bar p. And so this all amounts to just 1 over m times the expectation value of p. Right? And so that works because if I go up here and I take a time derivative of this, that's pulling out a factor of omega. And also there's a minus sign from cosine, the derivative of cosine. And so I indeed get the expectation value of the momentum once I divide by the m there. Okay, and then similarly, Ehrenfest theorem says if I take the time derivative of the expectation value of P, I get minus I over H bar. Expectation value of the commutator of P with the Hamiltonian, which in this case is the commutator of P with 1/2 m omega squared x squared. Okay, and more generally, that would just be V of x in general. Okay, and so this amounts to minus I h bar, derivative of the potential with respect to x. And so the whole thing is minus the x derivative of the potential in expectation value, which here is minus m omega squared times x. Okay, so again, both of those you can plug in for this coherent state and show that indeed Ehrenfest theorem works, as we proved on general grounds. For homework, what I'm giving you is a different state of the harmonic oscillator that's not a coherent state, and just asking you to show that in that state as well, Ehrenfest theorem works. Okay, but getting back to the coherent states, you can show, I'm not going to go through the details, but you can show that the wave function in a coherent state, so I'm labeling it by alpha, the complex number of the coherent state, which is equal to x alpha. You can show this is equal to the following. This is e to the I theta. I'll say what theta is in a minute. And there's a normalization factor, m omega over pi h bar to the 1/4. There's another exponential of I times the expectation value of P times the number x over h bar. And then there's another exponential, which is minus the number x minus the expectation value of x squared over 4 times the uncertainty in x squared. Okay, so what is this theta? So e to the I theta is a constant, not like this phase up here. This phase was an irrelevant phase, but it wasn't a constant. This e to the I theta down here is a constant phase, but it's also irrelevant. Because it's a global phase, it's multiplying the whole wave function. And it's actually equal to, it turns out, the real part of the complex number alpha times the imaginary part of the complex number alpha. That's what theta is. Okay, other things are delta x here, we worked out last time, is very small. Right, we're in a state that's very sharply peaked around the classical values. In fact, how small is it? It's square root of h bar over 2 m omega. And of course, whenever you have an h bar, that's going to make it a small number for macroscopic things. And then the expectation values of p and x are the classical values. And so if you want, you can now put in the time dependence for them, and you can have the wave function at any given time. Okay, so the fact that we have a very small delta x means this is a very sharply peaked Gaussian. This factor is telling you that this thing is moving with its classical momentum. This e to the I theta is something you can just drop because it doesn't affect anything. And the rest of this is just a normalization to give it unit norm. Okay, so that's one way of writing it. Another way that's exactly equivalent is you can also write it as basically the strategy here is to write it in terms of the ground state wave function. So psi alpha of x is same irrelevant phase, the same momentum phase, okay, and times the ground state wave function of the harmonic oscillator, but evaluated not at x, but at x minus its expectation value. Okay, so this is where psi 0 of u is the normalization factor, and then the Gaussian factor, which is just telling you that's the ground state wave function. But unlike the real ground state wave function for this system, which is centered at x equals 0, this is being evaluated at a point that's offset by the expectation value of x, and therefore it's oscillating back and forth as the expectation value of x is oscillating back and forth. Okay, and so the reason the ground state wave function is appearing in this formula is sort of that this thing is so sharply peaked that its expectation value or its uncertainty in xnp is the same as if it were in the ground state, but now the ground state's moving back and forth. The ground state wave function is moving back and forth. Okay, so then just to mention for homework, one of your tasks for homework is to find the overlap between beta and alpha for two different coherent states. And your job is to write this as the exponential of something. You are assigned the task of making sure that something is in the simplest possible form. But because it's the exponential of something, it actually doesn't matter what the something is. You can conclude from that that it can never vanish, because for no complex number is the exponential of something equal to 0. And so what that means is the probability, if you're in the state alpha, of finding yourself in the state beta is equal to beta alpha squared, which is always non-zero. This is also the exponential of something, which you should put in simplest form. Okay, and this is true for any two coherent states. Okay, and so this is saying the coherent states are not orthonormal. Which is consistent with the fact that they're not eigenstates of a Hermitian operator. They're eigenstates of the lowering operator alpha, which is not Hermitian. Okay, questions on coherent states before we move on to something else? Okay, so one thing you can do is for any system, not just a harmonic oscillator, you can construct, in principle, these quasi-classical or coherent states. It turns out that for any other system other than the harmonic oscillator, it's much more difficult to construct the coherent states. The harmonic oscillator is very special and very nice that you can construct these things easily, or relatively easily, as we've done over the last lecture and a half. But in principle, you can do this for any state. All right, now we've been talking about the one-dimensional harmonic oscillator, but of course we live in a three-dimensional world. And so we should say something a little more practical about a 3D harmonic oscillator. Okay, and so first of all, the Hamiltonian for a three-dimensional harmonic oscillator consists of a kinetic term, which is 1 over twice the mass, times the three-dimensional momentum squared, which I can write like this. The sum of the three x, y, and z momentum squared, plus now there's a potential, which is 1/2 m. And then there's a different frequency in principle for the x and y and z directions. So I can write this as omega sub x squared times x squared plus omega sub y squared times y squared plus omega z squared times z squared. So when we first started talking about the harmonic oscillator a few lectures ago, I mentioned that basically any potential that can be approximated by a harmonic oscillator, but one thing that could happen is you might find cross terms between x and y. And what we've done here is we've eliminated those by choosing our coordinate system so that they don't occur. And to give you practice in how that works, homework problem 1 of homework set 7 is actually taking a more general harmonic oscillator Hamiltonian and rewriting it by a change of coordinates so that it has this form, where there are no xy or xz or yz cross terms in the potential. All right, so our job now is to find the stationary states of this Hamiltonian. And before we do that, it's a good idea to think about what they might look like. So first of all, we could ask about the symmetries of the problem. And one possible symmetry is translations. And the thing is, this Hamiltonian is not invariant under translations. So we should not expect our stationary states to be eigenstates of translations. Why is it not invariant under translation? Just because if I move along x, y, or z, I'm going to be, so x, y, and z equal to 0 is a special point. That's where the potential vanishes. And if I move to any other point, it will be positive, this contribution. And so that's certainly not a special point. Okay, so more formally, the way you would say this is you would construct the three-dimensional translation operator and sandwich the Hamiltonian in between it and its Hermitian conjugate. This is not equal to the Hamiltonian back again, which it would have to be if it were formally invariant under translations. Okay, but it is invariant under a different symmetry, and that's parity. Just like the one-dimensional harmonic oscillator was. Okay, so the parity operator times the Hamiltonian times the parity operator back again is equal to the Hamiltonian. And you could just sort of read that off by the fact that everything involves things squared, right? And so if I flip x to minus x, x squared doesn't change, p sub x squared doesn't change. And so the fact that it's invariant under parity means we should be able to find stationary states that are also parity eigenstates. So we know that going into it. All right, so now the way to solve this is divide and conquer. We write our Hamiltonian as the sum of three Hamiltonians, one for x, one for y, one for z. Notice that the reason we want no cross terms between x and y and x and z, etc., is so that this will work. And h sub x here is just 1 over 2m p sub x squared plus 1/2 m omega x squared times x squared. Okay, and that's the one-dimensional harmonic oscillator Hamiltonian. So we can go through all the steps that we did for the one-dimensional harmonic oscillator Hamiltonian. And we know that we write this as h bar omega sub x times ax dagger ax plus 1/2. We just have to slap an index x on everything so that we are distinguishing this part from the y part here, which would be, and the z part here, which will be handled the same way. Okay, and so in particular, in doing that, the operator x is equal to square root of h bar over 2m omega sub x times a sub x dagger plus a sub x. Okay, and p sub x is I square root of h bar omega sub x m over 2. Notice the m doesn't need a subscript x because there's only one mass. We're only talking about one specific particle here. But this is multiplied by ax dagger minus ax. And then similarly for y. So y is square root of h bar over 2m omega y times its creation operator plus its lowering operator, okay, etc. for p sub y, z, and p sub z. Okay, so one of the reasons this works is because these Hamiltonians, h sub x, h sub y, and h sub z all commute with each other. So this is where one would have to be careful in a more general situation. You might divide up your Hamiltonian like this and find out, oh, the three parts of it don't all commute. But because these all commute, we can find an orthobasis of common eigenstates. We had that theorem that said that was possible. Okay, common eigenstates for each of these operators. And so they're defined like this. H sub x acting on a state that we're going to label n sub x, n sub y, n sub z. Those are the number of quanta in the x, y, and z Hamiltonians. This is equal to the energy eigenvalue, E sub x. And then similarly for H sub y, it's acting on the same state here, but now it gives back the different number, E sub y times that state. And same for H sub z. Okay, it gives back E sub z times this thing. Okay, and the nice thing about this is we've already solved these three eigenvalue problems. We already found the allowed eigenpairs, and they're given by these integers, n sub x, n sub y, n sub z, which we know, I'll write j generically for x, y, or z. These have to be non-negative integers by exactly the reasoning that we've already gone through in the one-dimensional case. And then the numbers, the eigenvalues, oops, I'll just write it as j here, are h bar times the corresponding frequency, which can be different for x, y, and z, times the number n sub j, and then we can't forget the 1/2 0-point energy. Okay, so this is true for each of j equals x, y, and z. Okay, now one thing one might want to do if one has such a stationary state is do something like evaluate the expectation value of some function of x. And the best way to do that is to not write this in terms of Hermite polynomials, which one could do, but instead to write everything in terms of creation and annihilation operators. And so, for example, if I want to know what a sub x does to one of these stationary states, basically it just acts on the n sub x and ignores the n sub y. So we can read off from what we had before that this will be square root of n sub x. And it lowers the n sub x number by 1 but it just ignores n sub y and n sub z. Similarly, if I do a sub x dagger, acting on one of these states, that will be square root of n sub x plus 1. It will raise the n sub x number by 1, and it will ignore the others. And for example, if I do a sub y, now it will ignore n sub x, but it will multiply by square root of n sub y, and it will raise n sub y by 1. Oops, lower n sub y by 1. Okay, etc. So the more formal way to do this is in terms of tensor language, but tensor language means just what you would think it would mean. It just says that really the state n sub x, n sub y, n sub z, you can think of as this thing called a tensor product of the one-dimensional harmonic oscillator eigenstates. Okay, but unless one is doing some mathematical proof where you need mathematical rigor, there's no real point in writing it like this when you could just write it like this without the funny circle multiplication signs. Okay. The other thing is that the operators h sub x, h sub y, and h sub z are a complete set of commuting observables. So this set of operators is a complete set of commuting observables. And so we can convince ourselves of that pretty easily. One is they're observables. They're Hermitian operators. Okay, they commute with each other. And the last thing we need is that they have to, the second C says, actually the first C says they must uniquely specify the state if you know their eigenvalues. Okay, so once you know n sub x, n sub y, n sub z, and you say that's my state, then there is no other state with those same eigenvalues. We proved that basically by proving in the one-dimensional case that it was true. And so once we put these together, it'll still be true for the general state. Okay, so now you can talk about, if you really want to, and sometimes it is useful to be able to talk about the wave functions for this set of orthobasis states. Okay, and that's going to be psi. I'm going to put a label n sub x and another label n sub y and another label n sub z. And it's a function of position. This is defined to be the inner product of the position eigenstate R with the stationary state n sub x, n sub y, n sub z. Okay, and all this is the product of the one-dimensional things, but one has to be a little bit careful because the one-dimensional things don't have just different n's, they also have different omegas. Okay, so I need to put a little label that says n sub y here and omega sub y. And then here's n sub z, oops, n sub z, omega sub z of z. So in particular, when these things are built out of Hermite polynomials, there was this change of variables to go to the dimensionless quantity. And one has to be careful that one uses the appropriate omega when one does that. Okay, but these are just the solutions of the one-dimensional harmonic oscillator problem with the appropriate omega sub x, omega sub y, or omega sub z. All right, so one thing we can do now is consider a special case of this where the omegas are all the same. That'll be more pleasant because then we don't have to worry about getting confused between the different omegas. And that's called the isotropic three-dimensional harmonic oscillator. That just means all the omegas are equal. And so I don't need a subscript anymore to distinguish them. I'm just going to call them all omega. So this has a special property that there's nothing special about the x direction versus the y direction. And so this thing is invariant under rotations. Around the origin. So that means there's a new symmetry that we're going to have to worry about. The symmetry under rotations. That's going to manifest itself in a discussion of angular momentum, but for now we're going to pretend we don't know that. And we can just ask, what are the eigenvalues of the total Hamiltonian? Okay, and so now it's still labeled by 3 integers. The energy eigenvalue is. But now I can pull out the common factor of omega, and I just get n sub x plus n sub y plus n sub z. Each one of those came with a plus 1/2. So now there's plus 3/2. And whatever this n sub x plus n sub y plus n sub z is, it's a non-negative integer because I'm summing up 3 non-negative integers. So this is a non-negative integer, which we're just going to call plain n with no subscript. And so what we notice is that now in this case, the energy eigenvalue doesn't depend on the 3 integers, it only depends on 1 integer. And so there's a degeneracy involved here. Okay, and so we can label our states instead as n. That'll tell us the energy eigenvalue. But then there's a degeneracy in the energy, so I need a label for that, which I'm going to call rho sub n. Because for different n's, there might be different degeneracy labels, as we're about to see, actually. Okay, so now we can find a new complete set of commuting observables. As a general fact, the complete set of commuting observables is rarely unique, or almost never unique. And that's going to involve the total Hamiltonian as one of them. And the others are going to involve angular momentum in a way that I'm not going to specify immediately, but we'll come back to that. So I'm using descriptive language here rather than being precise about what my angular momentum operators in the complete set of commuting observables are. So in preparation for that, though, we'll just start by figuring out what's this degeneracy label. And in fact, what is the degeneracy label of each energy level n? So an energy level just depends on what the one integer n is. And we want to know what's the degeneracy of n. Which is also the degeneracy of E sub n. Okay, so let's just do a few examples. Suppose we're in the n equals 0 level. There's only one way that can happen, and that's if all three of the integers are in fact 0. And so in that case, there's no degeneracy. So G sub 0 is equal to 1. Remember, G is our generic notation for the degeneracy. Maybe if I go up to here, I should say that rho sub n takes on the values 1 up to G sub n. G sub n is the degeneracy. Okay, so for the lowest level, there's only actually one way to build such a state, and so the degeneracy is 0. But now let's say we're in the n equals 1 level. Okay, and now there are 3 ways to build such a state. We could have n sub x equals 1, and n sub y equals n sub z equals 0. Or n sub y equals 1, and n sub x equals n sub z equals 0. Or obviously n sub z could be 1. But that's the only 3 ways to do it, because if any of these is bigger than 1, you can't get down to the level 1. Okay, and so here the degeneracy of the level n equals 1 is equal to 3. Okay, so let's continue on. Suppose we're at the n equals 2 level. By the way, you're going to get to do something like this for homework, except in the case of a not isotropic harmonic oscillator in 3 dimensions. So at the n equals 2 level, one thing you could do is you could have one of the n's be 2 and the others be 0. Okay, but it could be n sub x, it could be n sub y, it could be n sub z. So there are actually 3 permutations of this that work. The other thing you could do is you could have 2 different ones be 1. Oops. So n sub x and n sub y could both be 1, and n sub z could be 0. And once again, there are 3 ways to do that, because basically you're choosing one of them to be the one that's 0. And so that's giving you a total of 6 possibilities. And so the degeneracy of the n equals 2 level is 6. All right, let's just do one more, and then we'll do the general case. If we're n equals 3 level, so what could we do? We could do one of them be 3, and the others be 0. Okay, and there are 3 ways of doing that. Basically choosing which of the 3 gets to be the one with 3 quanta in it. Or we could do nx equals 2, and one of the others be 1, and then the last one is 0. And there are 6 ways to do that. 3 times 2. And then finally, you could choose all 3 of them to be 1. Right? And there's only one way to do that. And so the total number of ways you can build an n equals 3 state out of the individual complete set of commuting observables, eigenstates, is 1 plus 3 plus 6 is 10. Okay, so G3, the degeneracy of the n equals 3 level is 10 here. Okay, so now now that we have some experience, we can do this in general. We want to count up the number of ways that you can take any integer n and decompose it into the sum of 3 non-negative integers. And there's a nice trick for doing this called the dots and lines trick. Okay, and so the idea is you draw n dots in a row. Those represent the different quanta. And then you separate them by 2 lines so that you're separating them into three groups, and those three groups are the n sub x, n sub y, and n sub z. Okay, and so it might look like this. Okay, and then some more dots, and then some more dots. I've drawn 2, 4, and 3, but in general, this would represent n sub x. This would represent n sub y. This would represent n sub z. And so by drawing 2 lines there, I've separated them into 3 groups. And now I just count up how many possible ways are there to divide them up this way. And the number of ways is the same as the number of ways of arranging n plus 2, n dots in 2 lines, things in a row, which is n plus 2 factorial. But then n of them are identical, so I divide by n factorial. And 2 of them are identical, so I divide by 2 factorial. Okay, so I'm just counting up those. And so the degeneracy is that number. G sub n in general is n plus 1 times n plus 2 divided by 2. Okay, and now if you want, you can plug in n equals 0, 1, 2, and 3, and see that it reproduces the numbers up here that we already got. So that's going to be a clue when we deal with everything in terms of angular momentum, because when we do it with angular momentum rather than x, y, and z, we need to get the same degeneracy at each level. And so we'll have to see how that works. Okay, so our goal here is we want to use a complete set of commuting observables, which will consist of the total Hamiltonian and then in some way to be specified, the angular momentum, and maybe something else. It will turn out not that we don't need something else when we deal with the angular momentum in the correct way. But the angular momentum, if it's going to be part of the complete set of commuting observables, should distinguish between the otherwise degenerate states. So this should distinguish the n plus 1 times n plus 2 divided by 2 degenerate energy eigenstates. And so that'll give us a way of checking that we really do have a complete set of commuting observables. We know what the degeneracy at each level is. And so if we have found a CSCO, then it must be true that it's uniquely going to determine which one is which from among that set. Now we could do this for just the the three-dimensional harmonic oscillator, but it turns out the same issue is going to arise in lots of other problems. So we might as well use a method that's not tied specifically to the harmonic oscillator. And so we won't. Okay, so there are lots of other applications for the technology that we're going to develop. So I'll just call it angular momentum technology. And so they will include, notably, one of the classic problems is the hydrogen atom. You can also apply this to the free particle. We've already studied the free particle, but we're going to study it again when we study it in terms of angular momentum eigenstates. And then finally, there's something called intrinsic angular momentum, which is going to, again, use the same technology of operators that we're going to develop for angular momentum. So this is otherwise known as spin. Okay, and that'll sort of come along for free once we've developed this technology. Okay, so we are now going to be doing angular momentum for our next topic. We're done with the harmonic oscillator for now. We will return to it later. Okay, and so classically, a reminder that what does angular momentum look like? It's r cross m times velocity, which is r cross p. And so all we're going to do is promote this to a quantum operator. L, the operator, is going to equal r, the operator, cross p, the operator. And if you take the cross product, the x hat component is y p sub z minus z p sub y plus z hat z p sub x minus x p sub z. Oops, that's the y hat part. What am I saying? Okay, plus z hat times x p sub y minus y p sub x. Okay, notice that the x hat, y hat, and z hat are not operators. These are just constant unit vectors that are pointing in what we've decided to call the x, y, and z directions. That's why they're lowercase. There's nothing operator-like about them. They're just constant vectors. But everything else in there is an operator. And so, in fact, this we will call the x component of the operator L. This is the y component of the operator L. That's the z component of the operator L. And so the whole thing is x hat L sub, x hat L sub x plus y hat L sub y plus z hat L sub z. So one thing to notice about these is, in general, when you multiply two operators together, you have to worry about the fact that the things you're multiplying together might not commute, and therefore it matters what order you write them in. And so is it a Hermitian operator or not? But for the special case of this that we're doing here with angular momentum being multiplied together, that doesn't arise. And that's because as operators, okay, the commutator of x with p sub y, for example, x and p sub y both occur in L sub z, but they commute. And similarly, this is equal to y commutator with p sub x. And because they commute, the ordering doesn't matter. So I'll just write et cetera here for every other combination that occurs there. So the ordering in each term does not matter. That's where it's important that we're taking the cross product here. If we defined an operator that was like r dot p, then the ordering would matter, and we'd have to be a lot more careful, but angular momentum is nice and doesn't care. All right. So the next thing that we're going to do when we start on Monday is to show the following fact. We're going to show that the operator L sub z is in fact the generator of rotations about the z-axis. It's traditional to start with L sub z, partly because it has a nicer representation in spherical coordinates. But of course, the same will be true about L sub x, about the x-axis, and L sub y about the y-axis. So this is the generator of rotations about the z-axis. And this is analogous to a fact that we already showed, the fact that P sub z, the ordinary momentum, is the generator of rotations, of translations along the z-axis. Okay, so next time we will do that. We will then study in more detail the eigenstates and the eigenvalues of angular momentum. And then having done that, we will return eventually to the three-dimensional isotropic harmonic oscillator and check that everything works. And in fact, that we get back this degeneracy at each energy level as a consequence of the fact that it's invariant under rotations, and therefore that the eigenstates of energy are also eigenstates of angular momentum. All right, so that's where we're at. And I'll stop the lecture there and ask if there are any questions.
Professor, I have some questions from the notes.
Okay.
I can let others ask questions if they want to ask first, because mine is from the notes.
Okay, any questions specific to today's lecture?
I had a question.
Sure.
So when we were using the we had degeneracy of like rho sub n, and then we went to g sub n, and I was wondering what the difference between those two are.
Ah, good. Okay. So so I think that the key thing to keep in mind here is this. Oops. Okay, so rho sub n is a label telling you which of the degenerate eigenstates you're talking about. And g sub n is the total number of them.
Okay, that makes more
So
that makes
rho
sense.
sub n is an integer that runs from 1 up to however many there are that are all degenerate with each other.
Okay.
Okay, so this is the key thing. And so if you're asking how many degenerate eigenstates are there with some energy, you're asking the question, what is g sub n? And
Yeah.
if you're saying which one of them am I talking about, that's what rho sub n is.
Okay, thank you.
Good. Okay, other questions about today's lecture? All right, let me turn off the recording.